Hi, everyone. Today we are going to moving on into a couple of additional topics that expand our understanding of the physical world. So we started out with the particle model of motion, and we did forces and dynamics on particles. And the last unit we've been covering rotations and working on extended objects. And today we're going to talk about what happens when you have solid objects that actually change their shape. So we'll be moving into this topic that's called stresses and strains. And stresses and strains is the topic that describes what happens when rigid bodies, which is kind of what we've been dealing with so far, start to change their shape under applied forces. So by implication, what we've been doing is something that the object is just kind of given as a fixed object, and when the forces act on different parts of it, they create torques around the centers of around the center of mass, and that center of mass motion we describe with the particle model. But now we can actually start to describe what happens if those forces actually squeeze or twist or shear the objects. And we use all of these we approach all of these under the framework of something that's called Hooke's law. So Hooke is named after the British scientist and describes the general relationship for the deformation of solids. Now, we've been dealing with this in Hooke's law in the context of springs, and we often call that Hooke's law. But that's a general representation of that's a specific representation of a more general relationship that is described here as stress over strain is equal to an elastic modulus. And these are all new words, and we should sort of describe what they mean. So to start off, stress is referring to the forces that are deforming an object. And this requires both an understanding of the forces that are pushing on the object and also the geometry, usually the area over which those forces are being applied. The strain is the resulting change in shape of that object. And this is almost always expressed as a fractional change. It can be a change in a length relative to another length, or we'll also deal with changes in volumes of objects. And it's always the change over the original volume. And then finally, there's this elastic modulus, and that has different forms depending on the types of strains and stresses that we're discussing. But elastic moduli are constants that are properties of matter. And we're going to go through three specific cases, three types of deformations, and each of those is going to have their own elastic modulus and their own framework. And I think the best way to approach this is through examples. And the first example that we will deal with is what's called a tensile deformation. So tensile strains and stresses correspond to the stretching of a solid object by pulling on a force that is perpendicular to its length. And you can think of tensile, it's related to the word tension, and it's just the same kinds of forces that we think about in terms of tension. And much like a tension force, tensile forces, we think about both of those forces applying to each end of the object and pulling it outward from the middle. And we describe a tensile stress as this force perpendicular, so perpendicular to the sort of area at the end of the object, divided by the surface area. And so this is like a little wire or a cylinder or something like that. And the relevant variables are how long it is originally, that's L naught. This length L is what it will stretch to, the perpendicular forces, and these are, you use one force, F perp, for the forces applied at both ends. So much like a tension has the forces at both ends that are applying to it, this counts for, you don't write down two force perpendiculars when we think about tensile strength. It is just the equal force applied on each end to this object. And if you write those down, dimension the surface area, this is the cross-sectional area of the object involved. That's A. And so a tensile stress is just the perpendicular force divided by the area, and the tensile strain is the fractional change in length of the object. And so that's the new length minus the original length divided by the original length. Now, stresses, you'll notice, are forces over areas, and those are units of pressure. More on that in the next video. But for now, pressure is expressed in the SI unit of Pascal, which is just 1 Newton per meter squared. You might know that an atmosphere is about 100,000 pascals, and that corresponds to 100,000 newtons of force applied to every meter squared of area. So we have 1 PA is 1 Pascal. So we then take all of these variable definitions and we turn them into a relationship which describes the stress over the strain. So that's the F perp over the cross-sectional area divided by the fractional change of length over the original length. And this gives me F perp over A times L naught over delta L. And all of that is equal to a constant. This constant is called Young's modulus. Modulus just means like some sort of constant property of matter. All of these things are moduli, so plural modulus is a moduli. So Young's modulus is just one of the many moduli of matter. And it's a property of the material that you're looking at. So aluminum has a Young's modulus of 7 times 10 to the 10 pascals, or 70 gigapascals. And copper is has slightly more tensile strength, and so it has a higher Young's modulus of 1.1 times 10 to the 11 pascals, or 110 gigapascals. Okay, so how do we go through and apply this? Well, we have an example here with a weight that is suspended from a ceiling. So we have a ceiling up here. We have a 500 kilogram weight. It's attached through a circular steel wire. That's this part here, with a diameter of 0.50 centimeters. The wire is used to suspend this 500 kilogram mass from the ceiling, and we want to know how much does this wire stretch. So it should stretch. We're given a Young's modulus for steel is 200 gigapascals, and we will assume G equals 10.0 meters per second squared. So this is an application of the previous formula. And so this just gives us the perpendicular force. Let's thicken up our lines a little bit. So F perp over the area is going to times the original length over the change in length is going to be equal to Young's modulus Y. And from that, we are going to just apply the variables. What we have been asked to solve for is the change in length. So how much does the wire stretch? Change in length. So what we'll do is solve this equation for the change in length. And so we get that the change in length is equal to the F perp over the cross-sectional area times the original length over Young's modulus. And now let's plug in some numbers. So the perpendicular force that's being applied downward is going to be the force at one end. And so that's going to be the mass times G of the weight that's suspended. So this is going to be the mass of the weight times G. The area here is going to be pi times the diameter squared over 4. So I give you a diameter. So pi d squared over 4 is the cross-sectional area of a circle. The length is what's given in the problem. And then y is Young's modulus. And now we just plug in all our numbers. So the mass of that is, from the problem, 500 kilograms. The weight is 10 meters per second squared. The length is 2.0 meters. Then we divide by pi times the diameter, which is 0.005 meters. Notice my conversion to metric on the fly. Squared, all divided by 4. Pop that into square brackets. Divide by Young's modulus, which is 2.0 times 10 to the 11 pascals. And we put all this into our calculator and grind, 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 crunch, 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 and out comes 0.00254 meters, or 2.54 millimeters. So thin little wire, so 5 millimeters in diameter, suspending a 500 kilogram mass from it, and it just stretches a little bit, 2.54 millimeters. So, tiny little bit just from the actual stress. But it does stretch a little bit, and then we can actually measure this from our see that length. We could actually measure it with meter stick from the extra force that's applied. Okay, so that's basically the framework that we're going to use for all of our problems. We'll often disguise what this is, but fundamentally, every one of these problems is know the formula, given everything or deduce everything but one variable, solve variable for formula. Like, this is like classic high school physics types of problems, just with new equations here. So where you should have a warm, fuzzy feeling about our Young's modulus types of problems and recognize tensile strengths, Young's modulus. Okay, we can switch back and look at a different type of stress. This is called compressive stress. Now, compressive stresses actually use the same formula as tensile stresses, and the big difference here is that we are just pushing in on both ends, and so we're squeezing an object by applying forces on both sides of it that are equal to F perp, so it crunches down, and it's going to express the force required to crunch it in terms of the same equation here. So we take the stress over the strain is the perpendicular force over the area divided by the change in length over the original length. And that gives me a formula that looks just like this. But we have applied absolute values just to kind of imply that just because the length is going to get shorter when I crunch this together, then we want this to end up being a positive number. You could also think about this in terms of the original value and then defining perpendicular forces as being outward. So compressive forces will be negative and inward. I just like to put the absolute values on it so that we just kind of keep everything positive and well sorted. Okay, most objects, like the metals we've been citing earlier, have tensile strengths, so the ability to kind of resist stretching, that are equal, their Young's modulus is equal to their compressive modulus. So stretching them and crunching them kind of yields the same strain for the same stresses and just how they orient. But some building materials like concrete actually have lower tensile Young's modulus compared to their compressive modulus. So concrete resists crunching really well, but if you take a block of concrete and you pull it apart, it doesn't hold itself together very well. So it's an aggregate material and it tends to break up and pull apart as we separate it. So concrete's going to have different values. Again, problems are going to either specify or require you to find what these are, but it's just kind of an interesting thing because we start to get physics really well applied to all of the objects around us. Okay, so tensile stress, compressive stress, kind of two sides of the same coin here. Our next type of stress is called bulk stress. And this refers to changes in volumes from isotropic pressures. And isotropic is a physics word, 100%. It just means the same in all directions. And usually when we think about isotropic, we think about isotropic pressure. So it's a force that's applied on an object that kind of crunches it down in all directions. And fluids, which we'll cover next unit, are the things that are really good at applying isotropic pressures. Okay, so tensile stresses are one dimension. Bulk stresses are three-dimensional. And what this means is we are sort of squeezing down an object by pressing on all sides of it. And to make the math a little easier, I'm going to use a cube with kind of a side area A, and then I'm going to describe the force per unit area there as a pressure that's kind of being applied to the exterior surface. And as a result, this object is going to kind of crunch down and get smaller. And I'm going to refer to the strain there as the bulk strain. So it's going to refer to the change in volume of the object divided by the original volume. So again, it's a dimensionless number, but instead of being a 1D strain, it's a 3-dimensional strain. Now we go ahead and say crunch down, and we will get a change in volume from this bulk stress. Okay, so we have the same relation. Stress over strain is the elastic modulus. In this case, we call the elastic modulus B. That's the bulk modulus. And we use a negative sign here to indicate the change in volume. So if we increase the pressure, then we're going to typically have a decrease in the volume. So it's going to sort of press the object down to be smaller volumes. And so this is equal to some value B, which is the it's called the bulk modulus of the object. And using aluminum and copper, we see that the bulk modulus of aluminum is 75 gigapascals and 140 gigapascals for copper. These are all at about the same length of, or the same sort of physical scale as the Young's modulus. So it's really referring to the internal forces inside the object. So the pressure is usually expressed as the change relative to the background. We're doing most of our operations in a 100,000 Pascal environment. That's the atmosphere here. And so we'll talk about changes with respect to whatever the background pressure is. So all of these changes in volumes are referred to with respect to their original volume, and changes in pressure are referred to with respect to their original pressure. Okay, so we can then say, all right, what's the change in volume relative given a pressure and some properties of the material. In this example, we'll consider the case of water, and we'll express this slightly differently. We say that water has a compressibility of 4.58 times 10 to the minus 10 inverse pascals. And a compressibility is defined as the 1 over the bulk modulus. So if I give you a compressibility, you know that that's just an inverse bulk modulus. Okay, if 1 kilogram of water has a volume of 1 liter at the surface of the ocean, ooh, exciting chemistry fact, what is the volume of 1 kilogram of water at the bottom of the ocean where the pressure is 1,000 times the atmospheric pressure? So that's 1.01 times 10 to the 8 pascals. So we'll take our formula, which says that minus stress, delta P over strain, is equal to the bulk modulus in this case. And what we're going to want to do is solve this expression for the change in volume. So from there, we can go ahead and solve for delta V. So that's delta P times V naught over B is equal to the change in volume. And so the change in volume is equal to the new volume minus the original volume. And then I will solve that by moving the original volume over to the other side. So I get that V is equal to V naught minus delta P V naught over the bulk modulus. And then I'll factor out that bulk the V naught to get 1 minus delta P over the bulk modulus. And from here, I can just stick in some numbers. So we get that this is equal to 1 liter. 1 liter, I'm going to, I'll just leave it as 1 liter times 1 minus the change in pressure, which is 1.01 times 10 to the 8 pascals, minus 1.01 times 10 to the 5 pascals, all divided by that bulk modulus, which I have forgotten I expressed as a compressibility. So I'm going to multiply it as 4.58 times 10 to the minus 10 inverse pascals. So just multiplying by the compressibility is the same as dividing by the bulk modulus. And if I plug in all of my numbers, I come out with this answer being 951 milliliters. And so we crunch down, we get about a 5% change in the volume of water here. So water is actually pretty incompressible. It holds up itself up pretty well as we get here. The final type of stress that we want to talk about is called a shear stress. And that's kind of summarized in this diagram here, where we think about a three-dimensional object that instead of sort of pressing on opposite sides or from all sides all at once, we think about what happens if we kind of pull on the top while pushing on the bottom. So this is called a shear force, where you have kind of, as you move vertically, you have changing horizontal forces. So a shear is usually, as you move in one direction, there's a change in the perpendicular direction. And we think about this object as a surface area A on top and a height h, and it's going to change its kind of position here of the top is going to move by a position x if I kind of pull on both sides with a shearing force, F parallel here. And so the stress here, the shear stress, will again write down as kind of a bulk module, or as a stress in terms of a pressure. So F parallel over A, so the force applied to the top area versus or the bottom area here. And it's going to result in a shear strain, which is measured as the horizontal displacement x divided by the height of the object. And so that's going to give you the resulting strain. So it kind of depends, like if the object is taller, a kind of small fixed displacement is going to actually matter less. This is kind of a proxy for this angle here. So x over h, you can see, is related to the tangent of this little angle. And so, as before, we have stress over strain is the perpendicular force of the area divided by x over h, and we'll sort of rearrange that, and that's equal to a shear modulus. And again, for aluminum versus copper, we see that our shear modulus is about 2.5 or 25 gigapascals, I should say, and then copper is 44 gigapascals. So again, aluminum and copper have related shear moduli, with copper being a little higher than aluminum on basically all of the axes. So the internal forces of copper are larger than those of aluminum. Now, we can consider this case for concrete. So concrete has a shear modulus of 3 gigapascals. And so it's 3 gigapascals. Let's think about what happens to a building in an earthquake. So this is a concrete building. It's going to be 30 meters high. So that gives me my H of 30 meters. And it has a roof area. So this area up top is going to be 400 meters squared. The building is subject to shear forces. So that would be these parallel forces here. So the net shear force on this is going to be 800 meganewtons. So quite a lot of force pushing on the building. And what we'd like to know is how far will the roof of the building shear relative to the ground? So we want this little displacement here, delta x, under our earthquake. And so then we have our stresses over our strains. So we have F parallel, F said parallel, I wrote perpendicular, F parallel over the area times the height of the building over x is equal to the shear modulus. And again, we can solve for x, so we get x is equal to F parallel over A times h over s, and then we plug in the numbers as given in the problem. So this becomes 8 times 10 to the 8 newtons. The height of the building is going to be 30 meters. The area of the building is going to be 400 meters squared. And then the shear modulus here is just 3 times 10 to the 9 pascals. And this will all sort out to become 0.02 meters, or 2 centimeters, which is good. We have an earthquake and the building doesn't move too much. Okay. Great. So the last thing to talk about is what happens when things break. Now, all of these things hold for only relatively small deformations of objects, so fairly small strains. And you're sort of familiar with this because if you apply a larger strain to an object, it will start to deform. And a good example of this is something like a paperclip. Now, this paperclip here is made of probably steel, and so it has these kind of high Young's and shear moduli and everything. And you're sort of familiar that if I actually take a little bit and I give it a little bend to it and sort of pull it just a little bit, it actually returns to its original shape. But if I give it a much larger stress, it will actually bend apart and it will deform and it will retain its original shape, its new shape there. And so this is this idea that this Hooke's law formalism really only works for these tiny strains. So as long as I don't get much of a resulting change in the object, it'll spring back to its original shape wherever I left it. And typically those, it depends on the material, but those strains are 0.01 to 0.3. Remember, these are like fractional changes in the object. After that, the material will start to deform. And then if things are large enough, the material will break. So for example, we can describe this often as in case of tensile forces, we refer to this as tensile strength of the material. So as an example, if the stress inside aluminum is larger than its breaking stress, which is 220 megapascals, then the object, whatever it is made out of aluminum, will end up breaking. And the Young's modulus for aluminum here is 7 times 10 to the 10 pascals. And you can actually figure out what the max strain for aluminum is before it will start to break by taking this breaking stress. Again, you just find it in a table of materials and solve for the max strain by sort of switching strain, cross-multiplying the Young's modulus and the strain to get, and then set the breaking stress over Young's modulus to find the maximum strain for aluminum is 0.003. So we had like steel wire where the strain that we saw there was like 0.001-ish. And aluminum here, so that object probably wouldn't break because the Young's modulus for steel is higher than that for aluminum. So aluminum here, if you have an aluminum wire and you subject it to a strain that is larger than 0.003, the system will snap and break. And so this gives us a way to kind of describe how objects will respond to forces on them, including when they will deform and when they will start to break. Now, I'll fully admit, we're just a bunch of kind of dabblers in this over here in the corner of physics. A lot of this is the domain of engineering, and all of these rules that we're putting here together, there's a far more developed framework for design of structures, understanding how forces work, all of that. While you are in this class taking Physics 144, the engineers are over there learning all about Bulk's modulus and solving thousands of different statics problems here, because in engineering, you don't want things to move under a lot of circumstances. But this is just the tip of a very well-developed iceberg from our colleagues across the campus, and they sort of explore these things in a lot more detail with more formalism and many, many, many more tables. But this gives you a sense of how to take our simple models of going from particle model to rigid bodies to now deformable bodies and kind of make our physics progressively more realistic.